This video reviews the BIG OSPF Config Lab, and it's the biggest such lab to date. There's a lot to do and a lot to learn, so you're going to really want to use this review video. It'll help guide you through considering your config versus what I think the correct config is, and walk through the verification steps. And you can keep coming back to this video over and over as you work through this big lab project. Let's get into it. So you should do this lab after you finish the OSPF part of the book in this course. That's part 6 in volume 1, by the way. So you should do this lab. There's the direct link. It's also linked in the description to this video. So I'm expecting you've read the top half of the blog page, which is pretty lengthy. Maybe you've watched the intro video and you've attempted the lab in Packet Tracer, or at least you've attempted the first task, which is to configure OSPF on all 7 of the routers in the lab. Then you're here in this video and you're reviewing some things. Now, this is a fairly lengthy lab and it's got some complexity to it, so you're going to weave in and out of doing different lab steps and maybe coming to this video to review. So in this video, I break it down by task. The lab breaks things down by task, so the configuration tasks are numbered 1 through 6. It starts out by configuring OSPF and router IDs on all 6 routers, or all 7 routers rather. Then it moves on to optional tasks like metric tuning at task 2, default route at task 3, tuning some OSPF LAN timers at task 4, and then passive interfaces and point-to-point network types at the end. As far as the organization though, you should do each config task and then verify that task. So in this video, I follow that same flow. I'll tell you what I think the correct config is for task 1 based on the requirements. And then I'll show you Packet Tracer and show you the verification steps for those tasks. So that, say, you could do task 1 and complete it, and then go away for 3 days, and then move on to task 2 and verify that, and the organization of this video matches that. You can come back anytime and tackle the next task and review it here. But before I dive in, I want to talk to you about a few caveats with Cisco Packet Tracer. Now, version 8.2.2 of Packet Tracer has been around for a long time, and most of my config labs, I've used that version. There is a version 9.0 that's out, but for 8.2.2, which I used to develop this lab, and the file will open in version 8.2.2, there are some issues, and I'm going to walk through them real quick with you. These are listed on the blog page under known Packet Tracer issues, and if I find new ones, I'll list them there. But a couple of things to make you aware of. The show IP route command in Packet Tracer, it should list the prefix length style mask by each route, but it doesn't. It just omits the mask, all right? Turns out that is the one thing I'm going to tell you about right now that's fixed in version 9.0. The mask is finally shown, all right? The rest of these are broken even in the new version. For instance, the next 3 are about an issue with the show IP OSPF interface brief command. That command lists the mask in DDN format, and in Real Gear, it's listed in prefix format, for instance. In this same command, if VLAN interfaces, that is layer 3 VLAN interfaces, are present, it omits the VLAN number. So instead of saying VLAN 101, it just says VLAN. So you're left to guess what the VLAN number is. And it just uses the wrong wording. It uses the word point instead of P2P to refer to OSPF network type point-to-point. On to a new thing. When there's a VLAN interface, a layer 3 interface configured on, say, a layer 3 switch, iOS picks a bandwidth setting. Well, Packet Tracer picks that setting differently than a real switch would. And then when you're using OSPF, that means you get a different default OSPF cost, all right? So that's just a little difference to be aware of. Next up, yep, there's more. This is a weird one. So in lab, in router B12, you're going to configure this command, IP OSPF1 area 0 under a VLAN interface 202. And you're going to save your config, and you're going to save your Packet Tracer file, and then you're going to close Packet Tracer and go do other things because it's going to take you lots of visits to this lab to finish it. And when you open the Packet Tracer file again, this command's going to be gone from B12. Yep. So every time you get back in, you're going to have to go and add that config command back. I have no clue as to why it's happening, but you can imagine in making this long video, I've closed and opened files a bunch of times. Yeah, every time, got to add that command back. In general, the more you configure, the more likely you'll see quirks So save your file, reopen. That's a good way to overcome those. And then just a few others I'll leave for you to read to yourself. So be aware, Packet Tracer is a simulator. It's written by humans to act like routers, but it's not real iOS. You should be skeptical of the output, all right? So it's a good tool, but it's not a perfect tool. And I just wanted to make you aware of some of the issues relevant to this really big lab because it explores a lot of different things. Now, on to those configuration tasks. So let's jump right into task 1 to configure OSPF, all interfaces in area 0 with the router IDs supplied. Now we've got 5 obvious routers from the drawing, and these layer 3 switches, D1 and D2, or dist1 and dist2, as you see in the packet tracer file. Those are the 7 routers where you need to configure OSPF. So I'm including these layer 3 switches. When I say the word routers, I include those, all right? So here's a repeat of the detailed instructions from the intro video. And the only thing that's really subtle here is the network command. I said, use any network command you want, but if you want a challenge, choose to use one network command and use as few 255s in the wildcard as you can. All right, so I just painted you into a corner where on the routers that you're using network commands, which are the 4 routers on the left side of the figure, I've painted you into a corner where there's only one correct network command to use. All right, so that's the challenge there. Is just a brain puzzle to get you thinking about how to configure the network command. So let's look at core 1 and core 2, and we'll talk about that network command. So these are the 2 routers on the WAN edge over on the left. So router OSPF 1 on each of them. I told you to pick the process ID. It doesn't accept 0, so 1 is the lowest number that works. These numbers do not even have to match on neighboring routers. You could have used 1 and 2, so I just picked 1. We've configured the router IDs of 1111 and 2222 from that table on the previous page. You can rewind and look at those if you want. And then they've each got one network command. Now, notice the network command is 10.0.0.0 with the wildcard of 0, 255, 255, 255. Now, if you chose the challenge, this is the right answer to the challenge. So the challenge said use as few 255s as you can while matching all interface IP addresses with one network command. All of the interfaces in network 10. So there we go. Network 10 is matched there. So if we look down here at this list, these are the IP addresses on core 1 in network 10. So one of them starts 10.10, the other 3 start 10.11. All right. So the deal is there, we can only match those that begin with 10. We couldn't match the first 2 octets because they differ in the second octet. So with this logic, the network command matches just the first octet of 10, matches all 4 interfaces. OSPF will be enabled on all 4 interfaces. Same logic here with this wildcard of 0, 255, 255, 255. Down there on core 2, effectively the same config, just with a different router ID. Then if we move on to dist1 and dist2, it's the same concept with the same wildcard mask for the network commands here. One network command enabling OSPF on all 4 interfaces. Here's the list of dist1's network 10 IP addresses. Notice they differ a little in octet 2. So we couldn't match on both the first 2 octets. We could only match on the first octet with this wildcard. And each of them have unique router IDs. Then over at the branch office routers like B11, we give it a unique router ID per the table. In this case, it's 11.11.11.11. And then to enable OSPF on the interfaces, the instructions said use an interface subcommand, IP OSPF 1. The 1 must refer to the process ID you used in the router OSPF command. So these have to match. And we place the interface in area 0 here. So B11 has these 2 WAN interfaces. So we see the subcommand under the 2 WAN interfaces. And you can't see it in the drawing, but there's a link to the switch. So that's the G00 interface over here on the right. And that's the one connected to the LAN. And there's OSPF enabled there. Then moving on to router B12, it looks very similar to B11. We've got the OSPF process. We've defined a router ID of 12.12.12.12. Then under the 2 WAN interfaces and the 1 LAN interface on the right, we've enabled OSPF with the IP OSPF1 Area 0 command under all three of those interfaces. Here we see the three interfaces with their IP addresses. But with B12 in this design, it's also got some embedded switch ports that are in VLAN 202. So in addition to that, here on B12, we've got interface VLAN 202 with OSPF enabled. If you left that out, then B12 would not advertise about this subnet, the subnet that's off of VLAN 202. All right, so that's an easy thing to overlook in this config, so make sure you added that. Now, I'm not going to show you B21's configuration, but basically it's everything for the two WAN interfaces and the one LAN interface that you've seen in the other two remote routers, just with different numbers in there. So let's take a look at Packet Tracer. This is the file that's opened, and I have added configuration based on task 1 and task 1 only. All right. So a few things. The 7 routers are the 5 routers with the router hockey puck, core 1 and 2, and the 3 branch office routers with dist 1 and dist 2, which are configured as layer 3 switches. Now, the other switches use that same layer 3 switch icon, access 1 and 2 on the left, switch 1 and 2 on the right, but they are only configured as layer 2 switches, so don't let the icons throw you off. Those are layer 2 switches, so 7 routers. This big OSPF lab is focused on the things that do routing, those 7 routers where you've already seen IP addresses configured and you just configured OSPF, all right? So that's where our focus is for this, and we're going to start out looking at core 1 and 2. Now first, think about what OSPF neighbors core 1 should have. Well, it should be neighbors with dist 1, as well as the 3 branch offices, because core 1 has WAN links connected to each of those. So we'll start out by looking at core 1, and as you can see, I've done a bunch of commands already, but let's retrieve a few things and look at show IP OSPF neighbor and see that indeed core 1 knows about 4 neighbors, and the neighbor IDs are listed as 3333 and then these other 2-digit values. And as a reminder, 3333, that's dist 1's router ID, and 11111111 is B11's, 12121212 is B12's, 21212121 is B21's, the 3 branch office routers. So the correct neighbors are known and they've reached a full state. The neighboring router is the designated router in each of those cases. All right, so some good information there. Now let's take a look at some routes, and we'll start out with the connected routes here on core 1. Show IP route connected, and see we've got 5 connected routes. Now if we were to look back at the diagram, it's probably useful that you have the lab page open while we do this. We see we've got that internet link with its IP address that's outside of Class A Network 10. But then we've got these 3 links that follow a similar pattern starting with 1011. Those are the IP addresses or the subnets connected to the links that are the 3 WAN links, whereas this one is the subnet that's between core 1 and dist 1. Now, if we look instead at the OSPF learned routes, we get some interesting things here. First off, I know from memory from working with this lab that these first 2 routes subnet IDs are the subnets on the far left. That is, the LAN subnets to the left of dist 1 and dist 2. They're learned by core 1 from dist 1, and so we see the outgoing interface of gig 00. That happens to be core 1's outgoing interface to forward things to dist 1. And we see the administrative distance of 110. That's OSPF's default administrative distance, and the metric for these routes are 2. It turns out with default settings, the interface cost on each of these gigabit interfaces will be 1. So that's basically meaning 2 links away, right? So from core 1, out 1 link to dist 1, out 1 link into VLAN 101, and likewise out 2 links to get to VLAN 102 as well. So those are a couple of routes you see here. Then these next 3 destination subnets in sequence, the ones that begin with 10.1, those are the 3 LAN subnets on the far right of the diagram. And let me clue you into something I did with the IP addressing scheme here. Those first 5 subnets that you see listed, they have a single digit in the second octet, 10.0 or 10.1. And I did that on purpose to help me remember. Those are the ones that are in the LAN subnets. And all the transit links, the links between two routers, those have 2 digits in the second octet, like 1010, which are those routed links between core 1 and dist 1, etc., and 10.11, which are the WAN links, as it turns out. So, rather than memorize every last address and subnet, I gave myself a little bit of guidance here. Feel free to take advantage of that. All right, I'm looking at my notes about what else I might want to show you here. Oh, those OSPF costs. So if you do show IP OSPF interface brief and look out here about 2/3 of the way out, you see the cost column, and you can see a confirmation of the interface costs for each of those. And if you looked around the different routers, you'll see that as well. Now, continuing on that theme, I'm going to look over at Core 2 and do the same kind of commands. As you can see, I've done those before we started recording. So we should see 4 neighbors. The 3 branch office routers are neighbors because Core 2 also has a WAN link to each of those. And Core 2 is a neighbor with dist 2, whose router ID is 4444. It also has some connected routes. So show IP route connected will show those 4. So 1010 240 is the subnet between Core 2 and dist 2 on the left. And these other 3 subnets are the 3 WAN subnets between Core 2 and the branch offices. More interesting is the set of OSPF learned routes, where we see those same 2 far left LAN subnets that have a 101 and a 102 in the 3rd octet, reminding us that they're on VLANs 101 and 102 as far as the numbering scheme goes. And then routes to the 3 LAN subnets on the far right. Now, I didn't pause to talk about it before, but notice this route to subnet 10.1.10.0. It's got the subnet ID listed here, but then it's got via, and it's got 2 different vias, if you will, 2 different next hop routers listed. And what that's referring to is the fact that, hey, this router, Core 2, can send packets to B11 next or B12 next out the respective interfaces, all right? So in this case, because of the default metrics, there's a metric tie of metric 2 going through either of those routers, so we see that showing up here in the routing table. And one last thing here on Core 2, show IP OSPF interface brief, we see the cost setting of 1 on each of those interfaces. Next up, let's look at dist 1 and dist 2. Now, dist 1, it's connected to this VLAN 101 and 102, so it's got a VLAN interface. And it's also got these routed links from dist 1 down to dist 2, and dist 1 over to Core 1, and dist 2's got the routed link up to dist 1 and over to Core 2. All right, so they've got a similar topology, all right, reflected back and forth to each other. We'll start up here at dist 1, and clearly I've done a few commands. So show IP OSPF neighbor, it's got 4 neighbors listed, but it's a repeat of 4444 a bunch of times, which is kind of interesting. So first off, neighbor ID 1111, that's Core 1. There's a routed link from this layer 3 switch to Core 1, so we'd expect to see that neighbor. Probably a surprise to you was seeing 4444, which is dist 2's router ID, show up 3 times. If you look at the far right, we see gigabit 113. That's the routed link between dist 1 and dist 2. All right, so we've got a link where we can forward IP packets directly across it. But we've also got those 2 VLAN interfaces that both dist 1 and dist 2 are connected to. They send hellos, they learn each other, they become neighbors. So over both VLAN 101 and 102, they also become neighbors. And by becoming neighbors over all 3 of those links, they can learn that in the topology and say if that routed link were to fail, they could still forward packets to each other over either of those VLANs. All right, so it's a little bit different from what you probably saw in the examples you've seen so far in your learning. So just wanted to point that out. All right, other things to see. Show IP route connected. Here on dist 1, we've got the 2 subnets off of the 2 VLAN interfaces. We've got that routed link up to, this one's the one up to Core 1, the router. And this is the subnet off the routed link between dist 1 and dist 2, up and down in the figure. Then show IP route OSPF. There's a lot here. So everything from here down are routes to transit links between routers. And honestly, for the purposes of the lab, I don't really care. All right. And we're going to change the metrics anyway in the next task. But these top ones are kind of interesting. These are the 3 far right LAN subnets. And if we look at those, we see metric 3. So that's because all gigabit interfaces right now have a cost of 1. That's 3 outgoing interfaces away, if you will. They all have the next hop address, and they all have an outgoing interface of gig 111. It turns out from my memorizing the numbers and making these videos, that says from dist 1 forward to core 1 next. And then core 1's going to forward on to the various routers. All right, so that's the origin of those routes. Now let's go over to dist 2 and just briefly do something similar because we see the same pattern here. So show IP OSPF neighbor. Dist 2 is a neighbor with core 2 over that routed link, and a neighbor 3 times with dist 1. Dist 1's router ID is 3333, and its neighbors over the routed link and over each of the 2 VLANs, similar to how dist 1 was neighbors with dist 2 over those same 3 links, right? Then for the connected routes, here on dist 2, there are connected routes for the 2 VLAN interfaces, and then for the routed interfaces, 1 over to core 2, the router, and then 1 back up to dist 1, all right? And then for OSPF routes, ignoring the routes to transit networks, which per my numbering plan have double digits in the second octet, focusing on these LAN links, the via here, this address of 10.10.24.2 and outgoing interface, that refers to the next hop of core 2. So dist 2's routes to those far right subnets right now points through core 2, the lower of those routers. We're going to change that when we change the metrics here in just a bit. Next up, we'll do the same thing on B11, B12, and B21, the 3 branch office routers. So with B11, as you can see, I've already done the commands a few times. So show IP OSPF neighbor. With B11, we should expect to be neighbors with core 1 and 2, the 2 routers on the left side of the WAN, B11 being on the right side of the WAN. So here's core 2 and core 1 as neighbors. And then as it turns out, B11 and B12, both at the same branch office, are both connected to one common LAN. So they become neighbors, and 12, 12, 12, 12, there's B12's router ID. So those are the 3 neighbors I think you would expect to find here. What about connected routes here on B11? Well, here is the LAN subnet 10.1.10.0/23 off of gig 00. That's the one that it shares with B12. And then the last 2 are the 2 WAN subnets, by my convention using a double-digit number in the second octet to remind me that's a transit network. But those are the connected routes. Now the OSPF learned routes, we see a bunch of transit networks, but we see some familiar ones. The first 2 in the list, we see the 2 LAN subnets on the far left of the main diagram, 10.0.101 and 10.0.102. So those are the 2 subnets that exist on VLANs 101 and 102 respectively over there at the core site. And as you see, it's this style where we have the same destination but 2 different next hop and outgoing interface options. So what does that mean? That means from B11's perspective, 1 route runs through core 1 and 1 route runs through core 2. So it's a tie there for both of those routes. In fact, it's also a tie for B11's route to 10.1.14.0. Where's that? Well, it's the subnet down here off B21. So again, from B11's perspective, it can send the packets through core 1 or through core 2. And why is that? Because all these metrics keep tying. Notice 3 and 3. 3 outgoing interfaces with cost 1 each is what's happening there. And once again, you can confirm those costs with the cost column and show IP OSPF interface brief, and we're going to change that with the next configuration task, change the metric values. Next up, let's talk about B12, which is similar but has some subtle differences because we've got those embedded switch ports. So show IP OSPF neighbor shows us 3 neighbors. We've got core 1 on the other side of the WAN, core 2, router ID 2222, as well as B11 on the other side of that LAN. So similar to what we just saw on B11. Then as far as connected routes go, that's where we see something different. We see 3 similar connected routes plus a connected route for this VLAN 202 interface. All right. So to support those embedded ports, you configure them to be in some access VLAN. I chose VLAN 202 in this case. So then you create an interface VLAN 202 for your layer 3 parameters like IP addresses. That gives us a connected route into what is subnet 10.1.12.0 as you see there. All right. So what else do we have here besides these connected routes? Show IP OSPF, or excuse me, show IP route OSPF to see the OSPF learned routes. Let's take a look at those. Well, here are the 2 routes to the 2 far left LAN subnets, 10.0.101 and 10.0.102, as you see there. And it's 2 different routes to the same destination in each case, via core 2 and via core 1. Same idea we saw in B11. Likewise with the subnet down off of B21. Again, 2 sets of forwarding instructions through core 2 or through core 1. All right. Yes, we're still on task 1. Let's take a look at B21 for just a moment. Of course, I've done a few commands ahead of time. So looking at neighbors, B21 will have only the 2 routers on the other side of the WAN. Router core 1 and router core 2 with router IDs 1111 and 2222. We see we reached a full state. There you go. Now, as far as connected routes go, show IP route connected shows subnets for the 2 WAN links, and then the 1 LAN interface 10.1.14.0/23 is the 1 LAN subnet. All right. Then as far as OSPF routes go, that's where things get kind of interesting here. This is the simplest branch office. It's got 2 WAN links, and because of those default metrics, we've got 2 routes to the subnet for VLAN 101 on the far left, 2 routes for the subnet for VLAN 102 on the far left, and for the 2 subnets up at branch 1, we've also got 2 routes. In other words, in each case, from B21's perspective, the route to all those LAN subnets tie with the route through core 1 and another route through core 2. All right. Now, in the next task, of course, we're going to change the metrics a bit, and we're going to favor routes through the top, and you're going to see those routes change. So just one last look at those interface costs. Show IP OSPF interface brief. You're going to look in that cost column to see those change as a result of task 2. Task 2 requires a little planning, then a little bit of configuration. So first off, it told us to make the reference bandwidth match a 100 gig link. So we have to do a little bit of planning for that. And then once that's changed, to change the cost on these 3 links, these WAN links that emanate from core 2, to be twice of what they would otherwise be. All right, so starting with the reference bandwidth, here's the deal. The instruction said to make it match the same speed as a 100 gig link. And it turns out the reference bandwidth unit is in megabits per second. All right, so 100 gigabits per second is equal to 100,000 megabits. So the number you configure in the autocost reference bandwidth command in OSPF config mode is 100,000, meaning 100,000 megabits, and you don't put a comma in there or it will be rejected based on syntax. And you need to do that on all 7 of the routers. So if you use this command and you typed it in, you probably noticed it gave you a message back in config mode that said, hey, you need to do this on all the routers in your domain. So you should have done that on all 7. Now, once you did that, it's going to change the default cost on the various interfaces, and it's going to be 100. And the reason for that is the interface cost is calculated as the reference bandwidth over the interface bandwidth. And all these links, the physical links, are running at 1 gigabit per second. So on a 1 gigabit per second link, the bandwidth by default is set to the equivalent number in kilobits per second. Isn't that fun? So 1 gigabit is equal to 1 million kilobits. Reference bandwidth is 100,000 megabits. So if you just adjust the units to use the same units, a million kilobits is 1,000 megabits. So 100,000 megabits over 1,000 megabits, of course, that math is easier, gives us 100. So if you did a show IP OSPF interface brief command on these routers after doing the reference bandwidth change, you should see all the interface costs at 100. So then to override the costs on those links, you would go to each of these three interfaces and each of these three out at the branch offices and configure this IP OSPF cost 200 command. So at this task, I need to do a brief tangent. It turns out if you're running along doing lab and you save your config and then you open up the packet tracer file again, you will have uncovered a bug, at least at packet tracer 822. So here's the deal. Over here on router B12, if you do a show IP OSPF interface brief command and you look at the interfaces, we see the two WAN interfaces. Those are the 3-digit numbers in the interface ID. And the one physical WAN or LAN interface, gig 00, but it doesn't list that VLAN interface where you enabled OSPF. And the weirdness is you configure that interface subcommand under the VLAN interface and do a copy run start to save it and save your packet tracer file, close the file, open the file, and that command under the VLAN interface disappears. Isn't that fun? So I'm going to go add it back real quick. Interface VLAN 202, IP OSPF 1 area 0, just like you did before. And now it's back. And if I repeat that same show IP OSPF interface brief command, now the command shows up again, or the interface shows up again, and it's included in OSPF. So when preparing these videos, every time I'd close and open the lab file, I had to go back and re-add this into router B12 every time. And you will too as you work to the lab. So that's just a heads up on that. Now on to task 2, where we've changed the reference bandwidth as well as changing some interface costs. And I'm going to start on router B11 because it gives us the most straightforward look at the new routes that appear. So first off, if we look at the running config, whoops, I don't have one of those here yet, so show running config, and we scroll down to the bottom where the OSPF details are. Here's autocost reference bandwidth 100,000, and we should find that on the rest of the routers if you configured the lab correctly. Then show IP OSPF interface brief will show us the cost of 100 on the LAN interface and WAN interface, as well as this overridden cost of 200 based on our configuration on that gig 010 interface that's connected over to core 2. In that configuration, again from the running config, if we go down to gig 010, there it is, IP OSPF cost 200. So I verified that the configuration looks like it should based on that information. But what do the routes look like? So show IP route OSPF. Here's our routing table, and let's focus first on the two routes for the subnets on the far left of the diagram, that is the LAN subnets at the core site, 10.0.101 and 10.0.102. So there's one route, so to speak, one next hop and outgoing interface. And if you look at this number, 10.11.15.1, and this outgoing interface, that's the next hop address of core 1 and router B11's outgoing interface to reach core 1. In other words, these routes point to core 1. Why is that? Well, we increased the metric for the link down there to core 2, so the route that OSPF chooses is the route that uses core 1. There's no tie on those metrics, all right? And then if you look around a little bit further, we see this one, 10.1.14.0. That's the subnet that's down here on the bottom right in branch 2. It's one route, it's one next hop address and outgoing interface, again pointing to router core 1 at 10.11.15.1. All right. In fact, if you look around, most of the outgoing interfaces that point over WAN interfaces are pointing toward core 1 because the metric on that interface connected toward core 1 is lower at 100 versus the WAN interface connected toward core 2, which is 200. So let's do the same thing down at router B21 and look at the interfaces first, and we see the cost of 100 for the WAN interface to core 1, Cost of 100 for the LAN interface, but a cost of 200 for the WAN interface connected over to Core 2, meaning we're going to prefer routes that run over to Core 1. Not all will run that way, but just prefer those. And if we look at the OSPF learned routes here, and we look, most of the outgoing interfaces show gigabit 000, and a few cases where it's gig 010, that is the link over to Core 2. So it doesn't mean all routes will go through Core 1, just it's a preference because of that slightly lower cost on that link. In particular, the two LAN subnets over on the far left, 10.0.10.10 and 10.0.10.20. Next hop is 10.11.17.1. That's Core 1's IP address on the link from this router over to Core 1. And there's the outgoing interface on this router connected over to Core 1. Next, let's take a look at Core 1 for a moment. And let's look at the routing table here. Show IP route OSPF. And I'm going to dig down a little bit and first look at these two subnets that are on the far left, the two that exist on VLANs 101 and 102. And notice here, it's just one route. It points to from Core 1 down to dist 1. It's really the only path that makes sense there. So it's one route. But I want to focus here on the metric. It says 1100. Now, going back to the diagram here from Core 1's perspective, it's got two outgoing interfaces between it and the subnet. It's got the outgoing interface on Core 1 and then the outgoing interface on dist 1 into that subnet. So two outgoing interfaces, but a metric of 1100. So it turns out if we were to pop over to dist 1 and do a command that shows the interface costs, notice the interface cost on the VLAN interfaces is 100. So it turns out there's a mistake that Packet Tracer makes. These VLAN interfaces, with all the same circumstances on a real switch, these VLAN interfaces would be assigned a bandwidth setting equal to a 1 gigabit interface or 1 million kilobits. And it doesn't. It makes the bandwidth equal to as if it was a 100 meg interface. So it's artificially low bandwidth and artificially high default cost of 1,000. So that's why back here on the core router, we ended up with this seemingly large metric in the route. So if you felt inclined, you could go to those VLAN interfaces and say, hey, I'm going to artificially move the cost down to something more akin to a gigabit interface, maybe make it cost 100 if you'd like. You don't have to. It doesn't really affect the route in this case. I just wanted to point that out in this case. Continuing with router core 1, let's look at the routes to 10.1.10.0. That's the LAN subnet in branch 1 at the upper right that both B11 and B12 are connected to. Here we see two routes listed here on core 1 via 10.11.15.5 and 10.11.16.6. That is two routes, one through B11 and one through B12. Why is that? Well, those WAN links, there's no differentiation of metric. From core 1 to each of those branch routers, it's cost 100, all right? So we've got the equal cost routes running there. Whereas down here to branch 2, where subnet 14 is, if you will, there's just the one route. From core 1, he's got the one WAN link. Looking at the figure here, here's core 1, one WAN link down to B11. There's not two links from core 1 down to that site. So core 1 has this single route down here. All the configuration for this task happens on router core 1. ISP1 is totally pre-configured. It has this IP address, and that'll be the next hop address for the static route you configure on core 1. Now we need this static route on core 1 because then you configure another command on core 1, which means conditionally advertise a default route into OSPF, but only if there's some other default route known in the routing table. All right, so that's the config. Once it's all there, you can test by pinging or tracing to this IP address for this server that I put out there to represent some server in the internet. So there's our static route, IP route, and as always for a default static route, the destination is all zeros and the mask is all zeros. And you just give it the next hop address. Here we see it. There's the IP address of that neighboring router. then to cause the router to advertise a default route if some other default route already exists in its routing table. You get into router configuration mode and type this command, default information originate. That's the style of command that says advertise a default if this other route exists. If you wanted to always advertise a default, whether or not Core 1 knew a default route, you'd put this always keyword at the end. We didn't in this case, making it conditional on this route existing. So here we are back in Packet Tracer with the couple of config commands needed on Core 1 already configured. But just to confirm that, show running config. And if I scroll down toward the bottom, we see under router OSPF 1, we've got this default information originate command. That's the conditional command, and here's that IP route command we just talked about. So those should exist. So a show IP route command will reveal those. And if we look at the top, we have this gateway of last resort statement, and it lists the next hop address. So on this Core 1 router, it's the static route we just configured and its next hop address that we see here, 198.51.100.9. And that's the one we also see in the static route that shows up in the detail part of the routes. Here it's a static route. The destination is all zeros /0. The /0 is the prefix notation for the same mask as 0.0.0.0. And there's the next hop address. So there's the static default route. There's the notation at the top of the table. Now it's going to look different on any of the other routers that have learned their default route via OSPF. So I'm just going to pick one. Let's use B21 here and look at its routing table. So here's show IP route. And at the top, it says gateway of last resort, but it has a next hop address. Why is that? Well, from B21's perspective, it's got a next hop address, right? It's somewhere else in the topology. So this address 10.11.17.1, looking at the diagram from B21's perspective, that happens to be Core 1's WAN IP address on this link between B21 and Core 1. So going back to look at that gateway of last resort, there it is. Now look at the bottom. Here's an OSPF learned route. It's an E2 route. That's an external type 2. It's something we don't get into for CCNA. But it shows a route for 0000/0, meaning default. And it says via 10.11.17.1. So OSPF learned the idea of a default route. It calculated the next hop address, which is Core 1's WAN address in this case. B21's local interface to forward the packets out would be gig 000 to reach that. So what you could do is you could go to the rest of the routers and identify that route, see what the outgoing interface and next hop address is. But if you configured correctly up on Core 1, all the other routers should learn a route like this and you can confirm it and verify it. Additionally, you can use pings and trace routes at any point in this process for any of these steps, but here's a trace route to that internet server's IP address. And if we see it run through there, you can look at those IP addresses. 10.11.17.1 is Core 1's WAN address. 198.51.109 is that ISP router's IP address. And then the last one is the server itself. Next up, configuration task 4. And this task specifically says, do this on LANs. All right. So in this lab, what I mean by that is any interfaces connected to subnet 10.0.101, 10.0.102, 10.1.10, 10.1.12, or 10.1.14. All right, those are the ones. So over on the left, that includes interfaces VLAN 101 and 102 on both of the distribution switches. Both router B11 and router B12 connected to this subnet, only B12 connected to that subnet, and only B21 connected to 10.1.14. The goal is to just let you exercise how to configure the hello and dead intervals to these values that you see here. Now, there's no way to tell iOS to say, hey, use a multiplier times 5 seconds to come up with 15 seconds for the dead interval. You just have to configure the numbers. So here on the distribution switches, under interface VLAN 101 and 102, you just configure these two commands to set the hello and dead intervals to 5 and 15 seconds respectively on both of them. All right, so I'm just showing one box, but it's needed on both of them. If you did it on one and not the other, they would no longer become neighbors over that subnet, all right? Because one would have one set of timers, one would have another, and that's one of the things that causes neighbors to not become neighbors, or potential neighbors to not become neighbors, all right? Next up, the branch routers. So B11 and B12, they need to have matching timers. So B11 and B12, they both happen to use their physical gig 00 interfaces to connect to this LAN. So they've got these same settings, 5 and 15 seconds, respectively. Now, B12 also has a VLAN 202 interface because of these embedded switch ports that we're using. So that's how to configure those. And then on B21, it's also using its physical gigabit 00 interface for this particular LAN. There's the changing of those settings. Now, if you can see the different colors here, this VLAN 202 interface and B21's physical interface, I've got it in a different color. And that's because these happen to be cases where there are no other routers connected, so you're not in danger of harming any neighbor relationships. But in a later task, I'm going to say to you, hey, you can make some interfaces passive, and you'll make those passive, and it won't really matter anymore what the hello and dead intervals are, all right, because there won't be any hellos being sent, all right? So that's just something to keep in mind as you think through this with bigger picture in mind and how you might do things out there in the real world. So we're going to start over on dist 1 and look at its hello and dead intervals on its two VLAN interfaces that connect down here. And dist 1 becomes neighbors with dist 2 over VLAN 101 and VLAN 102 using those VLAN interfaces and over this routed link. But for this part of the lab, we only change the hello and dead intervals over the two VLAN interfaces, all right? So that's the context. So if we get into dist 1, and as you can see, I've done a few of these commands already, and we try this show IP OSPF interface VLAN 101 command on a real switch, that would work. And here in Packet Tracer, it's rejected. This command will work if you point to a physical interface, but it doesn't work with a VLAN interface here. So if we do it without the interface ID shown as VLAN 101 and just press return, we get all the interfaces, and it turns out the first couple are the VLAN interfaces, so there we go. So we see up here at the top, it's VLAN 101, and down here it's VLAN 102, and the next one, gigabit 111, is shown up already. So under the VLAN 101 section, about halfway down, we see hello is 5 and dead is 15 because we configured it. I configured that off screen. All the configuration from the explanation a few moments ago has been added. And then here under VLAN 102, hello and dead are 15 here as well. So I did the same thing over at dist 2, and I can go there and show you those with this same command. But if I hadn't done that on dist 2, these two switches, these layer 3 switches, would no longer be neighbors over VLAN 101 and 102. So let's just look at the list of neighbors here on dist 1, and we see 3 mentions of neighbor 4444, which is dist 2, and 2 of those are reachable over VLANs 101 and 102 interfaces, VLAN 101 and 102. So that's a confirmation. By the way, the state is full. So that's a confirmation that we're still neighbors with dist 2, and that's a confirmation that it's got matching hello and dead intervals, because if they weren't matching, they wouldn't become neighbors. As another demonstration, let's look at routers B11 and B12, which are both connected to switch 1 in the same VLAN, and they become neighbors over that VLAN, all right? So B11 and B12 should have been neighbors before and should now also be neighbors after you changed the hello and dead intervals. So if we do a few commands here and show IP OSPF interface, here with a physical interface on router B11, we see that command works, right? It's not rejected. And we also see the hello and dead interval are set to 5 and 15. If we go down to B12 and issue the same command, we'll see it's also set to 5 and 15. So they shouldn't have had any problems for that reason, at least, in becoming neighbors. So let's look at the list of neighbors here. And we see 11, 11, 11, 11, B11's router ID listed here on B12 in a state of full, reachable out its gig 00 interface, so confirming that the change was made on both of these. Now, just a quick review, the configuration, it's straightforward. There on the interface, there's gig 00, And we've got the IP OSPF hello and dead interval commands with 5 and 15 configured. So let's revisit the rules because your first task here is to choose. So this task is about the LAN interfaces, which are all the interfaces on the routers connected to this subnet, this one, this one, this one, and this one, 5 subnets. So let's start on the left. We've got 2 distribution switches, and they each have 2 VLAN interfaces for VLANs 101 and 102. And these 2 layer 3 switches become OSPF neighbors over each of those VLANs, all right? So the rules are that you choose where you make the interfaces passive, and you should not prevent any neighbor relationships from forming. Well, these 2 become neighbors over both of those VLANs, so you cannot make them passive. If you did, you'd see the neighbor relationships fail, and you'd realize, hey, I shouldn't have done that, all right, at least according to the rules here. Now, you can argue whether you want them to be neighbors over that LAN or not, okay? That's just a design discussion. But per the rules here in the lab, don't prevent them, don't make these passive, all right? Same thing happens between B11 and B12 on this link. Now, behind this blob is a LAN switch. Both routers are connected to the same LAN switch, assigned to the same VLAN. They become OSPF neighbors here. So if you made either of these interfaces passive, the neighbor relationship would fail, so we can't do passive on those interfaces. But B12 has some embedded LAN switch ports. It's got VLAN 202 configured for that. It's got an interface VLAN 202. It's the only router connected to that subnet, so we can make that interface passive. Similarly, B21 is the only router connected to this bottom right subnet, but it's more traditional. It's a physical link connected to a physical switch. It's the only router down there. So here are the 2 that we can make passive. The configuration itself, relatively straightforward. You just have to know to go to router config mode to configure it. So on B12, get into router config mode, passive interface, and list the interface ID. And on B21, same thing, except the interface ID is gigabit 00. So there's not a lot going on for task number 5. So let's go to B12, where we made the interface VLAN 202 passive. And the show IP protocols command is where you go to see the evidence of that. And there's a section right about midway down that says passive interfaces, and it lists the passive interfaces, and there's VLAN 202. Now, a quick look at show running config. If you look down at the bottom where the OSPF config is, we see the command passive interface VLAN 202. All right, so that VLAN interface, there are no other routers out there, so it shouldn't have affected any neighbor relationships. Similarly, down here on B12, it's a physical interface that's connected to switch 2. If I hover there, it's gig 1024 on the switch end, and it's gig 00. Here, if I hover over the cable, it'll show up gig 00. Here, I'm having dexterity issues. There's gig 00 there on B21. So if we do the show IP protocols here on B21, we see gig 00 listed as a passive interface. Now, just for fun, I'm going to go up to B11. Now, B11 is indeed a neighbor with B12. Its router ID is 12.12.12.12. Out its gig 00 interface. But if we make that interface passive, it should break the neighbor relationship. So let's do that real quick. Router OSPF1 and say passive interface gig 0/0 and watch for the log messages that appear. I pressed enter and it tells me the neighbor is down. If we do an end command and look at the neighbor table again, we don't see 12.12.12.12 anymore, so showing that passive interface then, there's no hellos, the neighbor fails, it doesn't get relearned. Woohoo! We're at the last config task of this monster big lab, right? So the lab said definitively make the WAN links point to point. So what does that mean? Say on core 1, it's connected to 3 WAN links, 1 each to each of the 3 branch office routers in this design. So what do? You go to the core router, and on its 3 interfaces, you configure them with this command, IP OSPF network point to point. All right, so not a lot to choose in the config command, you just add that. And then for each of the branch office routers on the individual WAN interfaces you see there, you get into config mode for each of those, and you add the exact same command. So there's the config. Now between core 2 and the 3 branch office routers, it's the same idea. I'm not going to show you separate information on that. And then I gave you the option to choose whether you wanted to use point-to-point on these routed links between core 1 to dist 1, dist 1 to dist 2, and dist 2 to core 2. And I chose to do that here in the demonstration for this video. So what does that config look like? Well, dist 1, it's got a gig 111 interface connected over to core 1 and a gig 113 connected down to dist 2. Same exact config command. Dist 2, same idea, same exact config command as an interface subcommand to change to point-to-point. Then on core 1 and core 2, they have physical interfaces as well, and we've got the same command there to enable network type point-to-point. So for task 6, we're going to start at core 1. Now core 1 has these 3 WAN links, and we changed those to be network type point-to-point. And I made the choice to also make these 3 routed links point-to-point as well. So 4 of the links, the 4 links that are enabled for OSPF off of core 1 are changed to be point-to-point interfaces. So let's start out with show IP OSPF interface brief to get a one-liner per OSPF enabled interface. And if you look out at the far right, you see this state column. And state refers to the network type. And it says point, so you'd think that means point-to-point. Now, it's a small difference with Packet Tracer. On real gear, it's P2P, in uppercase P2P. But you get the idea, right? It's point-to-point here. So that confirms on all 4 of these interfaces, it's been reconfigured to point-to-point. Let's see, show IP OSPF neighbor. Now, if we look at the 4 neighbors, first off, the ones that are double digits in each of the octet of the router ID, those are the 3 branch offices, 11, 12, and 21. And look at the state column. It says we've reached a full state, which is the final state if you're exchanging LSAs. But out to the right of the slash, it's just got this space and a dash. All right, so what does that mean? That means you're not using a DR, which is indicative of using point-to-point network type. If we had left it at the default of using a DR and a BDR, then you'd see whether the neighbor was a DR or a BDR or a DR other in that case. Now on this neighbor relationship with dist 1, whose router ID is 3333, again, it shows full, but no DR, BDR notation, so that's another confirmation that it's point-to-point. Then last one, show IP OSPF interface, and we give it one of the physical interfaces, like this WAN interface, gig 000. If you look a few lines down, you see network type point-to-point. That's another way to confirm the network type on an interface. Now on router core 2, it's basically the same idea. We've got 3 WAN interfaces and 1 routed link, this time over to dist 2. They're all 4 changed to be network type point-to-point, so I'm just going to do the same commands here. Show IP OSPF interface brief. In the state column, we see the state is point, referring to point-to-point. If we look at our OSPF neighbors, we see the first 3 lines are referring to the 3 branch offices. They're in a state of full, but with no designation of a DR or BDR. It just lists the dash, again, as a subtle way of saying we're using point-to-point. And likewise here in the neighbor relationship with router ID 4444, which is dist 2 over to the left. And then finally, this last command, we're looking at a physical interface that's OSPF details, and there's the notation of the network type being point-to-point. Now to show a contrasting example, we'll go over to dist 1. Now it's got this routed link up to core 1 and a routed link down to dist 2, so that's 2 links where we will have enabled point-to-point, and I've done that already. But it's also got those 2 VLAN interfaces connected down to these VLANs 101 and 102, and those we needed to leave in their natural state as network type broadcast. So let's take a look here. If we do our same 3 commands, show IP OSPF interface brief, we see that on 2 of the interfaces, we see a state and it says BDR. That's the local device's state, and it's as backup designated router in each case. All right. And then on the other 2, it's acting as point-to-point. Those are the physical links, gig 111 and 113, that are connected from dist 1. The top one's over to router core 1, and the bottom one's down to layer 3 switch dist 2. All right. So that's one difference that you see. Now, if we do a show IP OSPF neighbor, we see that our neighbor relationships that run over VLAN 101 and 102. Notice the interface column, VLANs 101 and 102 over there on the far right. we see the state in this state column is full/DR. That's a notation that tells us that we are indeed using DRs and BDRs with those neighbors, whereas these bottom two, those are ones for which it says full just with that dash, which is that subtle way to confirm, hey, we're not using a DR or BDR on these. Last up, if you do this command and look at one of the physical interfaces connected to another device, this time to core 1, we see the network type is point-to-point. But if we were to do that same command and refer to the VLAN interface, just to show you, it's rejected because Packet Tracer doesn't support it, a real switch would. But if we leave off the interface ID and just look up here, it's like, oh good, it gave us VLAN 101 as the first interface. And we can look down here and say our network type is broadcast, confirming that we left it as the default of broadcast. That's a long video, maybe one of the longest ever. If you want to find your way of what to do next in this free CCNA course, click on the CCNA playlist over on the left. If you're ready to review more about OSPF, click on the right and look at the part review video, which will give you some guidance for that. Hey, thanks for spending the time. I'll see you in the next video.